All right, we are on chapter 5, section 3, protein structure determination. So you can tell my video is not currently working, but that's okay. We are going to talk about in this section, right, once you've gotten your protein, whether you've made it, you've purified it, whatever you've done to get your protein, now you want to know what's its conformation, what's its structure. And there are really two primary methods for determining molecular structure. So you can do X-ray crystallography or nuclear magnetic resonance spectroscopy, which is NMR. So we're going to first talk about X-ray crystallography, and X-ray crystallography really started in 1957, so quite a long time ago. And its basic setup is that you shoot X-rays at your protein, crystallization of your protein, and you can look at how those X-rays are diffracted, and you can look at their intensity, you can look at their direction, and then you can use that to determine the three-dimensional distribution of electron density in your protein's atoms, right? So you get basically like this snapshot in time of your protein structure, because your protein is in a crystal, it's in a solid lattice shape, so you get one structure. Generally, NMR uses a high-strength magnetic field, and it detects nuclear spin properties of certain atoms, and from that you can deduce their relative positions in solution. So for NMR, your protein's in solution. For X-ray crystallography, your protein's in a crystal. So NMR gives you a little bit more, I'll say native information, but the problem with NMR is it has a size limit of 40 to about 100 kilodaltons. So NMR has a size drawback, right? So size limit. But X-ray crystallography has its drawbacks too. So we're going to talk about each one and why you would use each one and what information you can get from it. So X-ray crystallography, right? We said based on the diffraction of X-rays by our protein crystals. And that very first protein that was identified using X-ray crystallography was myoglobin. And so there are two main steps to X-ray crystallography. And your book like glosses over the very first one, growing diffraction quality crystals. Oh my gosh, growing diffraction quality crystals is probably maybe more difficult than our second step, just because the crystals have to be super highly ordered. So it must be highly ordered, right? And if they're not, your X-ray diffraction patterns are going to be all crazy, and so you won't be able to get any data from it. So you have to try so many different crystallization conditions until you get this quality crystal. And so sometimes that takes years to find the crystallization condition. I'm not talking about like days or months, I mean years. So then once you get that crystal, the holy grail of the crystal, right? Now you can determine the phases of your diffracted X-rays. And so that's what we're going to talk about. So let's look at exactly how this works. So in step one here, we have this X-ray beam, and we aim it at our homogeneous, perfectly crystallized protein, right? And so the beam is going to interact with the electron dense regions of our protein. So anywhere we have a lot of electrons, our X-rays are going to be diffracted, or they're going to be, their path is going to be altered, and they're going to be scattered into different directions. And so you capture those diffracted X-rays using an electronic X-ray detector, right? So that's great, and your book shows that. So the diffracted X-rays hit the detector, and so you get this one data right here. This is your one data set. Now, what you have to do is you then have to rotate your crystal. So you rotate crystal, and you run the experiment again, and you get a second one. You rotate the crystal again, you get a third. You rotate again, you get a fourth. So every time you rotate, you're getting another piece of data. Because remember, we don't want a two-dimensional shape from this, we want a three-dimensional shape. So you have to rotate the crystal successively at certain degrees. It's very, very precise. And then all of those measurements are combined computationally. So they're all combined on a computer. And you get this electron density map. And so the electron density map allows you to create a model of the protein. And that model is built by fitting the polypeptide chain into the regions of electron density. And a lot of times this is done with fragments of a protein, not with the whole protein. And so that you can see that this protein model cannot be the whole protein. That's tiny, right? So a lot of times it's done with fragments so that you can get high resolution of those fragments. But that comes with issues as well because you're not looking at the whole protein. So here's an example, right? This is nitroporin 2. This is a protein that's in the saliva of some blood-sucking insects, right? So when they did X-ray crystallography, what they revealed was that there was an iron heme group that binds to nitric acid. So here's our heme group right here that they identified. And when it binds to nitric oxide, it is going to affect the vasodilation of the host blood vessels, right? Because you think about it, an insect's trying to feed on you, right? So it wants lots of blood. And so it's actually going to secrete this protein that promotes opening of the blood vessels inside of your skin, right? So this wasn't done with the whole protein. This was again done with a fragment of the protein, but it still allows you to look at those electron dense regions and figure out which residues are in those exact positions, because you already know the sequence of the protein. You just don't know the orientation. So you can look at the sequence and know what's going to come next, and then just look at the electron dense regions and then fit in the residues in those electron dense regions. So it's still a good method and it gives you a lot of information. So when we look at NMR on the other hand, right, this is going to look specifically at a couple of different atoms and isotopes of those atoms. So hydrogen 1, nitrogen 15, and carbon 13. These all have specific magnetic properties, right? And so you can give short radio frequency pulses. So, short radio frequency pulses, right? And those pulses will actually perturb the nuclear spin of these three atoms. And you can actually monitor the return to ground state, right? So the spin is perturbed and you monitor return to ground state. So when you monitor that return to ground state, it's going to tell you information about the electronic environment of every single nucleus of the hydrogen, nitrogen, and carbon. And you can do this with many different proteins, but remember we said NMR has a size limitation, and it's limited because really large molecules take a long time to come back to that ground state. So it takes a long time for them to orient in solution. So that means that their signals basically average out or become lost, and it doesn't give you a lot of information. So that's why they're restricted to proteins that are less than 100 kilodaltons. And the other drawback of NMR is that you actually need a very high protein concentration. But when you do NMR, you get a lot of structures. So I know this isn't in your notes, but it's just a picture from your book. So this is figure 5.3 from page 237. So the advantage to NMR is that you're doing NMR with your protein that's in solution. So it's in its native conformation. And so you're getting a bunch of snapshots, right? Well, molecules aren't stationary. They're always kind of adjusting and moving, and sometimes you have large conformational changes depending on if it's binding to something or not. And so what you can see is conformational changes or fluctuations in the molecule while you're doing NMR. So what you see here is that this region, right, has lots of variation. Well, maybe that's really, really important for protein function. And you wouldn't necessarily know that using X-ray crystallography because the protein's stuck in one orientation. So there are drawbacks and perks to using either NMR or using X-ray crystallography. And I'll try to find some animations of both of these so that y'all can kind of see them, because plain pictures are kind of hard to understand. Okay, and I have one joke for you because this is a short video, so I don't feel bad giving you a joke. My joke for you is here. What did the worm say to her son? She said, "Where on earth have you been?" Ha ha ha. Okay, have a great day.